Hi, this is Mr. Yeager for AP Physics. We are on to the topic of circular motion today. This actually still falls under what we call translational motion, which is similar to linear motion, because the idea is the object is still changing its position. It's still changing its position over time, and therefore we don't want to call this rotation. We call this circular motion, following a circular path. So we're going to look at a bunch of different situations here. We're going to include force, acceleration, and velocity quite a bit. And then we're going to actually be able to look at larger scale situations like satellite motion. That'll be in a different lecture. So here we go. So we start off with a picture. All right, we have this girl swinging a pail around and around in a circle using a rope. All right, and so the question is, what is the centripetal force in the system? Okay, what is providing the centripetal force? So the first question is, what is centripetal force? Okay, we've never used that one before. We've never put it on a free body diagram or anything like that. So what does that really mean? Okay, and I think many people can figure out or know that the centripetal force is a force that points toward the center of the circle. Okay, centripetal itself basically means center seeking. Okay, so what is then creating that force toward the center of the circle? Well, you can talk about the rope. It must be the tension in it. All right. So therefore, do I call it tension or do I call it centripetal force? Am I allowed to use either one? It's basically what we're looking at here. But first thing there is we can identify that it can relate to a particular force. All right. Again, center seeking, centripetal. All right. But I want to clarify one thing here. There's actually no force known as the centripetal force. Okay? Centripetal force, and some AP teachers don't even ever introduce the concept, or the words, I should say, of centripetal force. Because it is not a force that actually goes on a free body diagram. You're not going to be drawing some sort of diagram going, you know, weight, normal, FC, centripetal force. That would not be correct. The AP committee will not accept that. Okay? Instead, what you are actually finding when you find the centripetal force is the net force. And it's the net force that acts towards the center. And that kind of helps explain this. We never draw net force on a free body diagram either. Okay? So we're not going to actually, it's okay never to mention centripetal force, all right? But it's a way to maybe help us go, okay, I'm looking at the force acting toward the center, and it's the F net, all right? So what we are going to try to do instead is, just like in that first diagram, we want to identify what is pointing toward the center, what real force points toward the center of the circle. So that's going to be, again, any of these types that listed here, and we're going to use that to then calculate the net force and anything related to the net force. All right? And in all of the situations we're going to look at, we're going to be looking at what's called uniform circular motion, sometimes abbreviated UCM. Very clever abbreviation. All right? And all that means is we're trying to do a scenario where you are spinning, or sorry, not rotating. You are moving that object in a circle at a fixed speed and a fixed radius. All right? So we are not looking at you trying to speed it up or slow it down, okay? Or to change the radius, like and release more rope. All right, we might look at what happens there, but the idea is you're always going to be looking from one uniform circular motion situation to another uniform circular motion situation. One speed, one radius. All right. So this diagram is basically showing again what is important about the centripetal force. And I mean, the example always given in elementary school is swinging a bucket of water around and around and around. Okay. The idea would be without the centripetal force, obviously you see the tennis ball on the left flying off the object, flying off the table. Okay, and that's because nothing is forcing it to continue going around the circle. It's going to continue moving in a straight line. While in the other picture, okay, and on the right-hand side, we actually have a normal force. It's a surface pushing it that's actually going to make sure it stays in a particular, following that circular path. So again, if you don't have that circular path, sorry, that force pushing on the object, the object itself should continue moving in a straight line, going back to Newton's first law. An object in motion will stay in motion, so it'll go in the last direction of the last force. All right. Here's another quick example. All right. Think about what happens as you turn right around a corner. Okay. When you start turning, all right, you're going to obviously, your body's going to go to the outside. But so what forces are involved here? Okay. What forces are going to help you continue moving around in that circle? And that's actually going to be friction. Frictional force is what's preventing the car from skidding out. The car wants to slide when it goes around. It wants to continue in that motion. All right. But the thing is, the frictional force is going to allow it to make sure that it doesn't do that slide. It continues moving in the correct direction. Okay. Now that leads us to another term which really doesn't come up too often, and that is what's called centrifugal. All right. And all I really want to say about centrifugal is basically the opposite of centripetal. Centrifugal is the outward seeking force. All right. And this is more related to Newton's third law. All right. Because the idea is, if there's a force pulling me into the center of the circle, there must be an equal opposite force pulling me out. Now, what would that be? Now it's a little bit strange again. It would be basically the opposite of the frictional force. Frictional force is the ground on, or the seat on young, I say ground on car force. So that would be the quote unquote centripetal center seeking force. The outward seeking centrifugal force would be the action of the car on the ground. But we wouldn't draw that. It's all coming from one particular interaction. All right. It's just how you look at that interaction. Is there anything that's going to help prevent it from continuing to go that particular way? If there's a force in, there must be a force out, and that's called the centrifugal force. All right. So I throw some questions in here at random. You'll probably obviously get these. Many roller coasters have constant speed, but their velocity changes. Why is that? Well, that's because even if you're going on a loop, what's changing the whole time? And that would be your velocity or your direction. Okay, so your velocity or your direction is changing. Okay, so that's why you would be accelerating. Okay, obviously around this. We've talked, that goes back to the very first unit. You can go a constant speed around a corner, you can't go a constant velocity. Okay, so the direction changes, velocity is that vector quantity. Okay, so looking at circular motion, what are we going to maybe have to calculate it with? We're primarily going to be focusing on velocity, acceleration, and force. All right. And the nice thing is there's a lot of always rules in these problems. First off, you can already notice the directions of all the different forces. Okay. Velocity is always going to point tangent. Okay. You can see right here, right here, right here. All right. Velocity is always going to point tangent to the circle. Again, the idea is if you release it, that object should continue moving in that last particular direction of motion. It will be released that way. Acceleration is going to point towards the center. That's because acceleration is related to net force, and the centripetal force is the net force. And these two always have to be together according to net force equals m times a, Newton's second law. So not only will acceleration point toward the center, but net force will also point towards the center. So net force and acceleration toward the center, velocity is tangent, always, always, always. All right, and that's the idea, is the acceleration is telling you which way it's trying to turn also, if you think of it that way. All right, so how are we going to measure the speed if we're moving around and around in a circle? Okay, especially if you're moving really fast. I mean, a lot of times obviously in class, what I do is I spin my lanyard around, and I say, try to measure how fast it's spinning. That's going to be very difficult to do. So instead, what we try to do is we don't look at like individual seconds. What we're going to look at is basically the time to complete one revolution, and that is called the period, capital T. Okay, it's not little t, capital T. The time for one complete revolution. Okay, so instead of counting and trying to go, okay, you went a quarter distance, You just sit there and count. You start the timer, count how many times you spin it, and then stop the timer and divide the two. Time over number of revolutions is what you're looking at here. So that's going to be used, and that's still in seconds. Okay, this is still a measure. This is still a measure of seconds, time, or minutes, or hours, or whatever. But that's what we're looking for there. All right. So that leads us to our first formula. Okay. And so let's take it, basically derive the formula. If we start with average speed, I'm going distance over time. But the thing is now I'm going in a circle. So that means the distance I cover is the circumference. Okay? Well, what does circumference equal? All right? Well, circumference is 2 pi r. Okay? So I plug that in. 2 pi r over t, that will be my speed. That is my velocity. All right? My average speed, my average velocity is basically what we would say there. Well, probably average speed. But 2 pi r over t, where r is the radius and t is the period, the time it takes to go one whole revolution. So 2 pi r over t still is distance over time, so still measured in meters per second. All right. Acceleration, all right, can be determined from one of two equations. And I'm going to let you go in and go ahead and have a good time trying to derive this particular formula. They're never going to ask you to derive it, but go ahead and check it out in a textbook. I'm going to just jump straight to it. I'm just going to tell you acceleration is v squared over r. On your formula sheet, AP formula sheet, it's going to be written like this. Okay, AC equals v squared over r. Okay, lowercase r. All right, so they add that little c there, telling you it's the center-seeking acceleration, centripetal acceleration. Now, this is the primary formula you're going to use. By all means, if you want to use this formula based on what they give you, if they give you r and t, it's the same formula. Okay, it's 2 pi r squared is equal to this 4 pi squared r squared. 4 pi, not r squared, but you get 4 pi squared r squared over r. And therefore one of the r's cancels out. I'm not going to deal with it again. This formula you hardly ever use, but if you want to go ahead and derive it, just plug in 2 pi r over t right here. Okay? That's where you get the numbers right there, 2 pi r over t. I'll be more official. All right? So again, acceleration will occur in the same direction as the force, all right, because it's related to net force. So can you go around a curve with zero acceleration? This is an old question. Of course not. Okay? Of course not. All right? What about a constant acceleration? The answer there would be no. Okay, technically. You're not going to have a constant acceleration. You can have a constant magnitude acceleration, but that's not going to be true either. Okay? Because what's changing for the acceleration at all times? Up here, it'd be pointing down. Over here, it's pointing to the left. So if the direction changes, so does the acceleration. Okay? You're always going to change because direction is changing. All right. So before we jump to net force, so we've covered velocity. Velocity is 2 pi r over t, and acceleration, v squared over r. All right. Now we need to figure out the net force. Okay. And the thing is, we can pretty much get our formula because net force is m times a. Okay, m times ac if I'm doing the centripetal force. But the thing is, there's an important kind of rule to follow with the net force and to calculate the net force if you need the individual forces. And what we do is the net force, again, is what's acting towards the center. But what we're going to do is any force that's pointing towards the center, we're going to call that being positive. We're going to call that a positive force. Just like you did with Atwood machines, if you're in the same direction of motion, we say that you are positive. So if you're pointing in the direction of the center-seeking force, it's positive. Any real force pointing away from the center, straight away from the center, will be negative. Any force not pointing toward or away from the center, okay, we don't need to include. They're not causing any sort of change in direction, okay? When you go around a corner like this, you need to figure out what's pointing in. Maybe it's F applied, and maybe there's some sort of F applied out. This would be positive, the other one would be negative. Any other force, maybe the weight's pointing down here, I'm going to ignore in my net force equation. Again, net force is going to equal m times a. I'm going to add a little c there, so centripetal acceleration. which equals the sum of forces. We still have to identify what real forces are causing the net force. And we're going to be able to practice a couple problems in just a minute. All right. So that leads us to the net force equation for in a circle. Okay, and you can see me kind of break this down. We have F net equals m times a. Let me get my pen back. All right, there's my standard formula. Well, let's just plug in v squared over r for a. So mv squared over r. That is the way that you will probably see it. Actually, they don't give you that formula on your formula sheet because they're hoping you can make the assumption to make that adjustment. A lot of people simply write it this way, mv squared over r, because you're multiplying the two top components over the denominator. Okay. This one I have never used, but is available. Okay, it is available if you want to really use that one. I feel like I would always end up calculating the a and then multiplying it. Okay, so be aware what everything means. A is equal to v squared over r. If you give me the a, it's m times a. It's still always back to this formula. F net equals m times a. It's just what is given to you. Do you want to calculate it faster? Put it all together, create a larger formula. That's fine. Okay? It depends on how you want to approach the problem. All right. So, as I said, certain real forces will create this uniform circular motion, will be the cause of the centripetal force. Tension, friction, and gravity are definitely common ones. There can be applied. I mean, there could be pretty much anything. Weight and normal can actually help cause the centripetal force, okay, at certain points on the loop. So any force can really be involved. Your job is to try to figure those out. All right. For this right here, the common question would probably be something simple like, tell me about the velocity, the acceleration, the force of all of these different objects. So what you see here is there's an object, I'm going to label them A, B, C, D, at different points on a rope, but they're all connected by the same rope. And so they're all rotating together. One revolution will be the same period for all of them. Okay? It'll take the same amount of time for the outside one to make it in as the inside one because they're all connected. So the question is, which one has the largest velocity? Which one has the largest? Rank them from largest velocity, largest acceleration, and largest net force. Well, the answer is going to be D. D will always have the largest velocity, and it will get smaller as you go in. So the largest velocity, if I rank velocity, it would be D greater than C, greater than B, greater than A. Why? D has to travel the most distance. That would be your answer. That would be a justification. Okay? D has to travel the most distance. Now, because of that, obviously, it's the same ranking for acceleration and net force. It's all the same. Okay? And that's because, obviously, greater velocity, formula would be, A would be v squared over r. Yes, it has a larger r on the outside, but you got velocity squared there. I think you're going to be okay. And same thing goes with net force. Then you just do m times a. Obviously, if it has the greatest a, it should have the greatest net force if all the masses are the same. All right. Another quick way to recognize this is just by drawing the vectors. If you draw the vectors and go, okay, here's the center-seeking vector for A. Here's the one for B. Here's the one for C. And here's the one for D. Which one of those arrows is the longest? That would be D. So same idea. So you can look at it from an equation standpoint or just from a free body diagram standpoint. All right. So let's finish this up with some problems. I'll be working through these basically at the exact same time. So how do I approach different types of problems for circular motion? All right. So you have a 150-gram ball at the end of a string revolving uniformly in a horizontal circle of radius 0.6 meters. The ball makes 2 revolutions in a second. 2 revolutions in a second. So what's the velocity? Okay. So if I start off here, I'm actually going to go back and forth a little bit. I think I can fit it here. Oh, my bad. I'm not done with that problem yet. Velocity is equal to 2 pi r over t. Well, 2 pi, the radius, well, what's going to be the radius? It's going to go, it says it, 0.6 meters. 0.6 meters over, I need the period. Now, this is where people make a mistake. I have a lot of people that plug in 2, but this is 2 revolutions per second. 2 revolutions per second. Period is seconds over revolutions. So what do? I inverse that, and that is 0.5. So the answer for this one should be, calculating it, 7.5 meters per second. All right, what's the acceleration? Acceleration is v squared over r, so what I do is I do 7.5 squared over r again. I don't change r, it's still the same, 0.6. And I get 90, I'm going to just round it, 94 meters per second squared. I get 93.75. All right. Why is the acceleration so much? Just because you're changing direction constantly. You're changing direction very, very quickly. So sometimes these accelerations will be very, very large. Don't be scared by that. What's the force? Well, that's just basically saying what's the net force. Okay. That would simply be m times a. And so 150 grams, 0.15 kilograms times 94 equals 14.1 newtons. So not that much force, but it's a very small object also. Okay? So just using all the formulas, nothing too special there. Let's try another one. The moon's nearly circular orbit about the Earth has a radius of about 384,000 kilometers in a period of t 27.3 days. Determine the acceleration of the moon toward the Earth. All right, so this one, same idea. It says we're solving for acceleration, which is v squared over r. You could use the formula 4 pi squared r over t squared if you really want. It's all your choice. All right. In my opinion, I'm just going to usually solve for 2 pi r over t and then plug it in. So I'm going to solve for the velocity first. So this would be 2 pi times a huge radius. That would be 3.84 times 10 to the 8th. And I change it into meters. I need to change this into meters. So it'd be 3.84 times 10 to the 8th. Over the period, which has to be in seconds, so 27.3 times 24 hours times 3,600 seconds gives me a giant period, 2, 3, 5, 8, 7, 2, 0 seconds. I mean, it makes sense. It's a long time. So then now I have to multiply all this. And I get that the acceleration of the Earth around the Sun is 1,023 meters per second squared. All right, we're going to just double check that one more time. Yep, 1,023 meters per second squared. We are flying. All right. Oh, that's not the Earth. That's the moon around. The moon is flying. All right. Problem number 3. I think I have 5 problems for us to try here. All right. If you have a ball tied to the end of a 2-meter string that you are revolving below the string at a 30-degree angle with the vertical. Ooh. Okay. Find the tension in the string, calculate the centripetal force, and calculate the speed that the ball is moving. Okay, this one's a little bit tougher. I'm going to have to go back to the regular board to work this one out. So let's see. We got 0.150 kilogram object and tied at the end of a 2-meter string, 30-degree angle with the vertical. All right, so what does this mean? What are we doing here? What this means is I have an object rotating below the string, basically going around and around the circle below the string, around and around like this, okay? And so this is actually how I have to draw this out, okay? And so that line right there is just a line. This is basically meant to be the center of the circle, okay? And so let me double check this. I know the angle with the vertical, it said it was 30 degrees. So there's my angle. All right, let me go back. 2-meter long string and 0.150 kilogram object. Okay, so mass is 0.15 kilograms and the length of the string is 2 meters. Okay, so how can I figure this out? I want to figure out the tension, the force, and the speed the ball is moving. Okay, tension, the net force, and the speed the ball is moving. The speed, sorry, thinking of it, velocity. Okay? All right, so this doesn't have to be done in any particular order, but let's go ahead and try to figure this out. So what I do first is, what is acting on this object? What I have is I have weight pulling down, and I have tension pulling up. And that's it. Those are my only two forces acting on this object. Okay? And so I can try to figure out the tension first, that's true, because I can go weight is equal to 1.5 newtons, okay? 0.15 times 10 is equal to mg, okay? And with knowing that, I know the vertical component of the tension. Technically, again, this is Tx and this is Ty. Weight must be equal to the Ty, okay? W will equal to Ty in this particular problem. So now that I know what the Ty is, 1.5, I can solve for the tension. If I look at this, I have the adjacent side, tension is the hypotenuse, and I can solve. This would be cosine of 30 equals 1.5 adjacent over t, and solve for t. T equals 1.5 over cosine of 30. Okay. And that equals, sorry, grabbing the calculator again. And some of you guys all know the trig function really well. T will equal 1.7 newtons. We got that. So now I want to figure out the net force that the object feels. Well, the net force is what's making it go into motion, and that would be the center-seeking force, which in this case must be the Tx. Okay? So the F net is equal to Tx, which I can solve for by using tangent, opposite over adjacent. So this would be 1.5 tangent 30. 1.5 tangent 30. Tangent 30 would equal Tx over Ty, multiply out the Ty. So the Tx would be 1.5 times 30 tangent. The net force is 0.87 newtons. So that's the net force. Okay? I just use trig. This is the adjacent side, that's the opposite side. Tx is what's the only force pointing toward the center of the circle that's being created below the string. And so then finally, last thing, it says find the velocity. All right, I'm going to erase a little bit of this if you don't mind. Okay, I'm going to erase this stuff down here so I left some space. Okay. How do I figure out the velocity? Well, the velocity would be related to the net force equation. F net equals mv squared over r. Okay. And so I just need to, I know what F net is. I know what m is. What's r? What's the radius? Well, that's where the length comes in, 2 meters. I actually need to do some trig again. If the string is 2 meters, that's the hypotenuse. Let me figure out the length of the radius, the length of the pointing toward the inside of the circle. So the r would equal, let's see this would be opposite over hypotenuse. So sine of 30 equals, sine of 30 equals Tx, not Tx, what am I doing? Sorry. Lx over 2. I just got to multiply that. 2 times 30 sine. Okay, that's 1. So Lx equals 1, which means the radius is only 1. All right. I got to give myself room again here. I'm going to erase all this stuff over here. Okay. And if I rearrange my formula, it would be V equals the square root of F net times R over F. And so I can do that. V equals the square root, my net force, what did I say my net force was? Silly me. 0.87 times 1 over the mass, 0.15. Let me take the square root of all that. 0.87 times 1 times 0.15, square root. The velocity of the object is 0.36 meters per second. All right? Big problem. Very, very big problem trying to put everything together there. All right? But that would be part of it. Okay? All right.